All right, so we're going to do dot products now. This is one of the first two multiplications for vectors. It's also called, AKA, also known as scalar product. And you're multiplying vectors. So there's nothing scalar about that. The thing that's a scalar is the result. So when you do a dot product of two vectors, you end up with just a number, a scalar. Okay, so that's important. And there's always a few people who do dot products and in the end give vectors, even on the final exam, which is a tragedy. But let's go ahead and do this in 2 dimensions. So if V like has an x1, y1, and W has an x2, y2, then V dot W, and I don't know, how do you know that's a dot product and not a multiplication? Well, it can't be a multiplication. It has to be a dot product. We use a cross when we do a cross product. So there's no scalar product that's implied here. You're multiplying two vectors. So V dot W, of course, is going to be x1, x2 plus y1, y2. And note that this is a scalar result. Okay. And of course, we'll do the same thing in 3 dimensions. There's no vector anywhere in that result. Okay, so straightforward computation though. So if V is 215 and W is negative 342, then V dot W is 2 times negative 3 plus 1 times 4 plus 5 times 2. So that's negative 6 plus 4 plus 10, and I think that's 8, right? So that dot product we'll see has a fair amount of meaning to it. The bottom line, we're going to have 2 multiplications. You have to think about how hard it is in 3 dimensions to do trigonometry. And because trigonometry involves figuring out angles, and it's just really hard to figure out angles in 3 dimensions. And it turns out that we can, when we do the dot product between 2 vectors, it tells us about the sine of the angle that separates them. And the cross product between 2 vectors, which we'll do next time, tells us about the, oh, I'm getting this backwards. The dot product tells us about the cosine between the vectors, and the cross product tells us about the sine between 2 vectors. So whenever we want to do a computation that involves a sine or a cosine in 3-dimensional space, well, for the cosine, you'll see us grabbing a dot product, and for the sine, you'll see us grabbing a cross product. and now trig is opened up, but using a completely sort of different language. Instead of expressing things in terms of sines and cosines, we express them in terms of cross products and dot products. And so it is these two products that do our trig for us in three-dimensional space. That is the importance of sines and cosines. If sines and cosines are important in math and physics and engineering, then dot products and cross products are important because they are sort of the keys that get us to the sines and the cosines. You'll see very rarely do we express relationships between angles using trig functions. We almost always express relationships between vectors using cross products and dot products, because again, those effectively become our sines and cosines. Okay. So let's go ahead and jump into the trig then. Let's go ahead and do a next section here, which is the geometry behind the dot product. Okay, so we're going to just say very simply that this is the law of cosines. Okay, so first off, let's just draw a triangle. And remember what the law of cosines is. This from trig. Okay, so let's have this be A. Let's have this be B and C over here. And then this angle, I'll just call theta. And the law of cosines just says that C square is A square plus B square. So that's Pythagorean. And then if it's not a right triangle, then there's another term. So minus 2AB cos theta. And it turns out that this expression is sort of like, well, you can write this in terms of dot products. Okay, so a couple of notes here. Let's go ahead and do this in terms of the vectors. So I'm going to rewrite, I'm just going to redraw this diagram. Okay, and instead of having an A, B, and C, I'm going to do a V here, a W there, and instead of introducing a third vector name, what I want to do is represent the difference, the third side as a difference from V to W. So if I have my vector, let's say go this, let's see, I want to do V minus W. So V minus W actually should go from W to V. So let me do a third color on this real quick. I think I'll just do it in blue here, and I'll have my barb going to the left. Like, well, if it would just let me. Okay, this way. Now remember, I guess I could take you back to the previous lesson. So let me just remind you how this worked. Looking for it. This one I think would do the trick right here. That you've got two vectors V and W. It doesn't matter whether it's 2 or 3 dimensional. The third side of that triangle is V minus W, but you need to know that V minus W goes from the tip of W to the tip of V. Okay, so keep that in mind. as we go back here and zoom back in, this goes from the tip of W to the tip of V. So this guy is V minus W. Okay. Okay, now, first I need a note. And that is if, let's say V has components, let's say X, Y, Z. Then the magnitude of V is the square root of X squared plus Y squared plus Z squared. That's using that Pythagorean idea that we talked about in the last lesson. Also, if we dot V with itself, let's do V dotted with V. So here you would multiply the X component of V times the X component of V, and then the Y's and then the Z's. So you would do an X times X plus Y times Y plus Z times Z. And of course, that's just X squared plus Y squared plus Z squared. Which you may as well note, that's the magnitude of V squared. Agreed?
Yes.
Yeah. So this is, I'm going to put this under never forget. Okay, that V dot V is the length of V squared. Okay, never forget. It doesn't matter how old you are, never forget. Okay, if you're on your deathbed and someone asks you, you'll know. Okay, I'll be there. I'll ask you, promise. No, I'll probably be dead. That's the way it should be. Now, so if we translate the law of cosines from the vector form of this triangle, this becomes, let's see, C squared is the magnitude of V minus W squared. So this would be magnitude V minus W squared. That's the C squared. Equals A squared. Well, that would be like the magnitude of V squared plus B squared. That would be the magnitude of W squared minus 2AB cos theta. This would be minus 2 magnitude of V, magnitude of W, and times the cosine of the angle that separates them. Okay. Fine. Next, what you want to do is recognize that the magnitude of a vector squared is the vector dotted with itself. So we could say that the magnitude of V minus W squared is V minus W dotted with V minus W. Okay, magnitude of V squared is V dot V, V dotted with itself, plus the magnitude of W squared, that would be W dot W. Minus, nothing I can do here is that other than write magnitude of 2 minus 2 magnitude of V magnitude of W cos theta. Okay. I will go ahead and make the note here that dot products distribute. That's a property that's in this lesson, but for now I'll just write it here. So I'll say they distribute like multiplication. That's the only thing that's sort of less than obvious. Okay, so if I was to distribute, just like I was multiplying like a binomial times itself, then I would have v dot v. You can't say v squared because that doesn't mean anything. This is a vector. Okay, so you can say v dot v minus, you maybe would do a v dot w, and then minus a w dot v. And then it would be plus w dot w. Okay, and then this would be equal to, on the other side, v dot v, oops, plus w dot w minus 2 magnitude of v, magnitude of w, cosine of the angle that separates them. Like that. I mean, I guess I could say that this is the magnitude. Well, another thing is what I'll do is add also, it's easy to show that v dot w is the same thing as w dot v. Okay, so I'm about to do that now. I'm going to write v dot v is the magnitude of v squared. Okay, I have a minus v dot w and a w dot v. Those are the same, so I'll just write minus 2 w, or v dot w maybe, like that. Okay, and then I have plus magnitude of w squared. That's w dot w. Okay, equals the magnitude of v squared plus the magnitude of w squared minus 2 magnitude of v, magnitude of w, cosine of the angle between them, like that. And then by subtraction, there's a lot that eliminates. So I'll go ahead and just take the liberty of sort of crossing out things that appear on both sides. That will subtract out. This will subtract out. We'll divide by a -2, but I'll do that in 2 steps. So now I've got negative 2 v dot w is negative 2 magnitude of v, magnitude of w, cos theta, like that. And of course, we can kill the -2's here. And so this is our identity. Okay, so v dot w is the magnitude of v times the magnitude of w times the cosine of the angle between them. Okay, so that's how you find the cosine between two vectors, basically. This is how you do trig with vectors in space. Okay, so, a couple of comments. So this is, I guess, a theorem. For any vectors v and w, and I don't even think I'm going to exclude the 0 vector because the equation is still true. Okay, you may not know what the angle that separates a vector from a 0 vector is, but it doesn't matter because you'll get 0 on both sides anyway. So we'll go ahead and say v dot w is magnitude of v, magnitude of w, cos theta. Okay, that's the first. To do, obviously, cos theta is v dot w over the magnitude of v, magnitude of w. And so you see, I'm evaluating the cosine of an angle without even knowing what the angle is.
Okay, I found this on the web for CN evaluating the cosine of an angle without even knowing what the angle is. Check it out.
I hope that ends up in the recording. Okay, you guys all right?
Yeah.
So I'm doing trig without the trig. It's just with dot products. And that is really the most important. That's why dot products are important now, is that they do your trig for you. Okay, and again, I'll be saying the same thing and writing something almost identical for the cross product, which we'll do next time, but with the cross product, we'll compute the sine of the angle for you. Okay, so these are the things that do your trig with vectors. I think I would also like to add that if very importantly, if v is perpendicular to w, then v dot w will be what? Now, so the only thing you need to note is that the theta would be 90 degrees. So what's the cosine of 90 degrees?
0.
Yeah, so you can see that v dot w is the magnitude of v times the magnitude of w times the cosine of 90 degrees, which is 0. So one of the ways we've determined whether two vectors are perpendicular is we just quickly check their dot product. Okay, so this is super important. All of this is super important. Orthogonality becomes one of the most important ideas in linear algebra, and it becomes super powerful. And we talk about orthogonality in contexts that have nothing to do with regular vectors as you normally think of them. But we think about orthogonality of wave functions in quantum mechanics, of eigenstates in quantum mechanics. And when we talk about orthogonality of functions, you'll do that in your linear algebra class, and it'll have to do with the dot product being 0, but there are no triangles or vectors that you draw anymore. But it's just this notion that the dot product is 0. And it turns out there's lots of dot products beyond what you learn in this class. And if there are dot products in other contexts, then there is a perpendicularity in other contexts as well. So the word orthogonal means 0 dot product. Okay, and in geometry, orthogonal means perpendicular. So I'm just gonna real quick share something here, just so you can see that this is just kind of a tip of an iceberg. But you're looking at a page in Wikipedia here, and I don't know, I can't really, well, I guess I could zoom in. I wonder if I squish it down like this, what that'll do. Okay, so this is what I wanted to highlight right here. You guys see what I just highlighted?
Yes, we can.
Yeah, okay, so I'm just going to read. It says in quantum mechanics, which is the study of subatomic particles, a sufficient condition that two eigenstates of a Hermitian operator, psi sub m and psi sub m, these would be states of a subatomic particle, okay, like an electron or whatever, that these states are orthogonal as long as they correspond to different eigenvalues. Now, what that means, you'll learn in a linear algebra class, but look at it right here. This means in Dirac notation that this inner product, you see it has the two quantum states here. These are just the states of a charged particle. You could think of it as the energy level of like an electron, that the inner product of these two states is zero. We would say they are orthogonal. And it turns out that that's just a really powerful idea. And you can represent any state of a subatomic particle as a sum of states that are all orthogonal to each other. Just like you in this class are representing vectors in terms of I, J, and K, all sums of three orthogonal or perpendicular vectors. We take that same idea where we break vectors down into perpendicular components and we apply it into much more advanced settings, where it doesn't matter what it is you're studying. The question is, can we break it down into orthogonal components? And so we do that in quantum mechanics, but we also do it in spectral analysis, where we'll take a wave from like a radio signal or something like that, and we can break it down into orthogonal component waves. And what it means for those to be orthogonal has to do with taking an integral rather than a dot product, and because the dot product of functions is an integral. You multiply the functions and you integrate them. And if the integral comes out zero, and then we say that those waves are orthogonal. And it's really powerful when you can represent a wave in terms of orthogonal components. It allows you to really process the wave, to find certain parts of the wave that you don't want. You can turn them down, turn other parts up, make them louder. And it's just signal processing is what it's called. And it's a huge part of physics and electric engineering, I should add. So a lot of you guys will see that, those of you guys that are going to be engineers will see some of this later on. So it's just a little teeny tip of a gigantic iceberg when we start talking about orthogonality. Any questions?
No, thanks for the tidbit.
Sorry?
I said no questions. Thanks for the tidbit, the little explanation of seeing going further. That was really insightful.
Yeah, well, yeah, and it's just, you're only beginning to get to a point where you're seeing that math is really huge. Math and physics and engineering, these are, the theory gets huge and super interesting. And I guess what I would just say is, if you ever get a chance to take a linear algebra class, that's a really good start. And then all of a sudden, once you master your linear algebra, and I almost like the 285 more than the 260 linear algebra, because it goes a little more abstract. And the more abstract it is, the better, because the more things it applies to. And then all of a sudden, with that under your belt, you can understand so many things in science and statistics and physics. It's all based on these vectors that we're opening up right now. All right, let's do an example. How are we doing for time? 8:13. So let's see what we can squeeze in before it's time to go. Okay, so first, I'm going to have V be 215. and W be negative 342. Okay. And then I want to find the angle that separates these. Okay, so we know that we're really trying to get down to this thing here. In the end, we'll take a cos inverse to find what theta is. Okay, but we have to compute v dot w and the magnitude of v and the magnitude of w. So there's a few steps to do this. So let's go ahead and do v dot w. So that's 2 times negative 3 plus 1 times 4 plus 5 times 2. These sound familiar. I think we already did this. Was that negative 6? It's 8, right? Okay, then the magnitude of v is the square root 2 square plus 1 square plus 5 square. So I get the square root of 30 there. And then the magnitude of w is the square root of negative 3 square plus 4 square plus 2 square. Okay, so I think that's 9, 16, 25, that's square root of 29, I think. Okay. And so we know that the cosine of theta, the angle that separates them, is v dot w over the magnitude of v times the magnitude of w. Okay, so this is 8 over the square root of 30 times the square root of 29. And then, you know, and if you want, you know, obviously you're going to take cos inverse. Okay. So, sorry, my bad. So theta is cos inverse of this. Okay. And again, I'd make sure you're in degree mode if that's what you want. Could somebody do that real quick? I guess I could do it, but let's have a couple of us do it. Anybody?
24.26 degrees.
You say 24? Why did you get 24 when I got 74?
Oh, sorry. I got 74.
Okay. Yeah. No, that's okay. 74.26 or whatever. So that's degrees. So yeah, we're doing trig. Cool. You can figure out the angle, but you don't usually need the angle. Normally, you'll want the cosine or the sine of the angle, right? I mean, in trig, when do you use the angle for its own sake? Not very often. Normally, you're making measurements on triangles, and that uses the cosines and the sines. So, you know, this whole process of finding the angle, it's sort of something we can do, but I just don't see us doing it very often. You might note that cos inverse outputs from 0 to 180. So the angle between two vectors is always acute or obtuse, I guess you should say. It's never bigger than 180. Okay, so it's never negative. Or greater than 180. Which kind of makes sense to me. You could do sort of, like let's say the angle is 20. Okay, I suppose you could say the angle between the vectors is also 340 if it's 20, right? You could go the long way around, but that's not what we mean when we say the angle between two vectors. We always want the angle is between 180. That's sorry, but between 0 and 180. Okay, any questions about that? So that's kind of important. We got that. There's a thing in here about direction cosines. I'm going to have you read this. It's not going to be on a test. It's kind of cute, but to be honest with you, I've never seen it anywhere except for on this page of this book. I've never seen it in any other book. So it just seems like a kind of a waste of time. It's cute. What I do need to get is these orthogonal projections. Okay, so let's go ahead and draw our scenario here. Okay, so this guy down here is A, and then up here is B, like that. Now, when I say an orthogonal projection, it's like you're casting a shadow. So I'm going to try and do a perpendicular from the tip of B down to the side of A. So this will be perpendicular to A. I'm going to try anyway. So something like this looks pretty good. Okay, and I want to figure out what the projection of B onto A is. Let me see if I can draw that in here. It didn't let me do it. That's good. Okay, so in green here, this is called the projection on, let me put it down below here, onto A of B. Now, to me, that just looks like a trig problem. Okay, so I think we could probably figure this out, started with trig and then move over to a dot product. And I think you can see it's a dot product because that's the side adjacent to theta. We'll go ahead and mark this as theta here, right? So the length of the vector, the short vector B, is the magnitude of B here, like that. And if I want to find out this projection, then I'm going to need to do a cosine, right? And by the way, the projection is called proj. Well, I better do it in green since I started that. So i.e. this is proj. I hate this notation, and I'm so sorry. Onto A of B. Isn't that lovely? So that's the notation for a projection. Oops. Okay, so let's talk first about the length of proj onto A of B. Okay, so I think that would be the magnitude of B cosine theta, right? You guys buy that? You okay? Is that all right? Now the cosine of theta, let's see here. This would be the magnitude of B. Now, let me see if I remember this right. The cosine of theta would be A dot B over the magnitude of A times the magnitude of B. Am I right about that? Isn't that the formula we came up for the cosine of theta? See, I'm doing trig without trig. I'm using dot products and magnitudes. And of course, there's a cancellation that can occur here. So let me cancel out the magnitude of B there, like that. Okay, so this is A dot B over the magnitude of B. Okay.
The magnitude of A.
Oh, you got me. How dare you? Thank you. Now this has a name. The length of the projection onto A of B is called the A component of B. I'll give you the notation. It's called comp A component of B. So it's comp sub A of B, the A component of B. Run out of space. Okay, so what I've managed with my trig was to find the length of the projection, but the projection is actually a vector. Okay, and it's the A component of B because it's that, if you look at B, I'm going to do something in really wide strokes right now that I'll erase. If you look at B, this is going to be hideous. B is this, well, I want it wider than that. So B is the sum of this component plus this component, okay? And the sort of horizontal component of B that's parallel to A is the A component of B. There's another component of B that's perpendicular to A, okay? But that's not the one we're working on right now. That we would get that using a cross product because that needs a sign, not a cosine. Make sense?
Yeah.
Okay, so we won't do the other component until we do cross products. So the A component of B is the length. Now the direction is what I need next. Okay, so the direction, ooh, that's too big. How are we doing for time? 8:29. Yeah, we'll just get this down and we'll call it a night. So the direction of the projection of A onto B should be a unit vector parallel to A. So that would be direction would just be A over the magnitude of A. Get that? Okay, so I've got the length of the projection up here, and I have the direction of the projection. And vectors are length and direction, so I need to combine those, and I would just multiply them. So the projection, let me see if I can get this all in here. Okay, so I'm going to draw a line and wrap this up by saying that the projection onto A of B is the length times the direction. Okay, so the length was A dot B over the magnitude of A. And then times the direction, which is A over the magnitude of A. Now this is really confusing. You have to recognize that this whole thing here is a scalar. Okay, and this guy right here is a vector. Remember, dot products are scalars. And that's not a dot product. That's a scalar product. Okay, so we need to be careful. Let's simplify this and say, first of all, it's A dot B over the magnitude of A squared. So we put all the scalars together and then multiply that scalar by a vector, which is just A. Okay, so we'll just call that a little theorem. And that is the projection onto A of B has a bunch of A's in it, basically. So you would say that's A dot B over magnitude of A squared times A. Okay, that's a scalar multiplication, so I'm not even going to draw a dot there. And then the comp sub A of B, this is the A component of B, is just A dot B.
Professor, what is it that it says on the top, on the left right there? The T, is that TH? Or,
Oh, theorem, THM, sorry, it's a
Oh.
theorem.
all right, thank you.
Yeah, my bad. I've been doing that forever. Okay, so you got these two formulas, and those will come up in the homework, etc., etc. All right, so we're going to continue with this. Next topic is work. Okay. Work is just defined to be displacement, and this is going to be the magnitude of displacement. Times the component of force that points in the direction of displacement. Okay, so and these are scalars, all right? And then we just draw a little picture here. So let's say this is a force vector here, like that. And then I'll do a displacement vector, like that. I'll use a D for displacement. That's just a path you've moved from one point to another, okay? And then what I really want to do is look at the component of force that's pointing in the same direction as displacement. So maybe I could just kind of cast a shadow here. So first things first, let me draw a shadow vector like this, and I want that to be perpendicular to displacement, like that. And then a projection of F down onto D would go in like this. Okay, so that red vector there would be projection onto D of F. Okay. And we just want to multiply the magnitudes of these. Okay. So if we just kind of go back to our formula here, the magnitude of displacement would be the magnitude of D, okay, times the magnitude of the projection onto D of F, like that. But the magnitude of the projection is just the comp. So let's backpedal a little bit here and say that this is the magnitude of D times comp sub D of F. What that means is the D component of F. Oops. Okay. And maybe we could look back at what the D component of F is. We have a formula up above for comp. So I'm just going to slide up here. So that's the A component of B. It's A dot B over the magnitude of A. So it's just the A that appears in here twice, the thing with the subscript. Let's go here and say, all right, this is the magnitude of D. And then the D component of F gets to be D dot F over the magnitude of D. Like that. And of course, that scalar magnitude of D is appearing here twice. So we can just cancel that like that. And just say, this is just D dot F. Okay, so maybe let's just state this as a sort of a definition. So So this is, I guess you'd call this a theorem, I don't know, or a definition, I don't know. So theorem would be if force F moves an object with a displacement of d, then the energy expended is called work. Let's just say the energy done on the object. Oops. Is called work. W, if you like. Now this is a scalar. And the work is d dot f, but I'll just write it f dot d here. Just like that. So you see how really this is a trig problem. Okay. To get this projection, there's a cosine, there's a theta here. And this projection here, you would do the magnitude of f times the cosine of theta to get this projection, the length of the projection. Okay. This is a trig problem, but we did it without trig. Okay, we did it with a dot product instead. So this dot product is this thing, whenever a cosine comes up, we're just going to do a dot product to get the cosine. Okay, and it just does it for us. So, let's just do a silly little problem here. So let's say an object moves at an angle of elevation, let's say an angle of, let's say 35 degrees up from horizontal. At a distance, let's say for 5, let's say, meters. Okay. The force which does this points up, let's say 75 degrees from horizontal. With a magnitude of, let's say, 10 newtons. Okay, so unfortunately, there's not a lot of help here. So we can draw this. We've got a force going this way and a displacement sort of going this way. And I'm not even trying to be accurate here. Okay, but the force is going to be, let's see, 10 newtons. So it'll be 10 cos 75 and 10 sine 75. Like that. And the displacement will be see here, the angle, oh, there is 35 degrees for 5 meters. So this would be 5 cos 35 degrees and 5 sine 35 degrees. Okay. Okay. And I don't know, I mean, you can work all this out if you want here, or you can do it when you're all done. I'm going to go ahead and put some numbers in here. Make sure you're in degree mode if you're going to do this. Anybody get an answer for this?
I got 38.3.
Thank you. So this is going to be 38.3. Now the force is in newtons, so in the distance, the displacement is in meters. So these are Newton meters. N is for newtons. Okay, so that's force in metric. Okay. And then M, of course, is meters. Okay. And then Newton meters is joules. Okay. So this is 38.3 joules. We just use a capital J. Okay, any questions about that? So in metric, work, oops, is Newton meter, which is joules. In imperial units, work, again, you're doing force times distance. So force is going to be in pounds and distance is in feet. So normally we do foot pounds. I have a torque wrench that does Newton meters, but it also does inch pounds. So I know sometimes it's inch pounds and sometimes it's foot pounds, but it just depends, right? But normally it's foot pounds for you guys. Okay.